Imagine two robots trying to work together, but they can't talk to each other. How do they avoid getting in each other's way, make smart decisions, and still succeed as a team? Multi-agent robotic systems depend on coordination, but in real-world environments, communication is limited by bandwidth, latency, and reliability. This creates a challenge. How can multiple robots coordinate most effectively? We explore this problem through the VEXAI robotics competition, where two autonomous robots must work together on a shared field. The robots are tasked with collecting red and blue blocks and placing them into elevated goals to score points. These objects are distributed across the field, so robots must navigate and avoid collisions and interference with each other. A team's success depends on coordination between robots. If both robots go after the same object or block each other's paths, they lose time and scoring opportunities. Effective teams divide tasks, share information, and adapt to each other's actions in real time. So, the real challenge is not just moving around the field, it is coordinating well enough to win.
This is where our robots, Rusty and Scrap, come in. To teach them how to play the game, we used reinforcement learning with a simulated environment. Instead of writing every behavior by hand, we let the robots learn through repeated simulation. They try actions, see what happens, and get rewarded or penalized based on the result. They observe the world through devices like cameras and position tracking sensors, which tell them where they are and what is around them. And instead of controlling every tiny movement, they make high-level decisions, like picking up blocks and scoring them in goals. We also trained Rusty and Scrap in 2 phases. First, they learned basic behavior and were penalized for invalid actions. Then, once they were stable, we removed those penalties and trained them to maximize their score. During training, both robots shared the same policy, which means they were learning from the same underlying brain. At first, they cannot talk to each other. They can still play the game, but they have to do it on their own. They look at the field, make decisions, and try to score points independently. And honestly, they aren't bad. They make choices that work well individually, but aren't always great as a team. So we wanted to see whether communication could help. In particular, we want to understand not just whether communication helps, but how different communication strategies impact their performance and robustness. To answer this, we compared 3 communication strategies. First, no communication, where each robot acts independently. Next, explicit communication, where robots share their full observations with each other. And finally, attention-based communication, where robots learn to selectively share only the most relevant information. These approaches represent different trade-offs between simplicity, bandwidth usage, and adaptability. Our goal is to evaluate how each method affects coordination, overall performance, and resilience to communication loss.
This is where Rosie became really important. Training reinforcement learning agents is expensive. It takes a huge number of simulated interactions, and when you want to compare multiple communication methods, that cost multiplies fast. Rosie lets us scale that up. We were able to run dozens of environments in parallel, train multiple strategies at the same time, and complete over 1,000 iterations in about 18 hours. Without that kind of compute, this project would have been much slower and a lot less ambitious. Rosie is what made it practical to actually test these ideas at a scale instead of just talking about them. So let's take a look at the results of each method. With no communication, the robots could still function, but coordination was weak. They scored quite a few points, but they were working against each other. With explicit communication, performance improved by about 10%. They had more information, and that helped them cooperate better. But there was a catch. They started to rely on the information from each other, so when we turned off communication after training, performance dropped sharply. Attention-based communication did a little better, scoring about 20% more points than without communicating. It improved performance more than explicit communication, but when communication was removed later, the robots stayed much more stable. They had not just learned to pass information back and forth, they had learned how to make better decisions without completely relying on each other's information. while still retaining the benefits of communication from training.
In the end, our results show that communication does help multi-agent systems perform better, but not all communication strategies are equally effective. Explicit communication can work well, but it may be too costly or inefficient for real-world use. Attention-based communication appears to be a more practical approach because it reduces the amount of information being shared while still improving coordination. Going forward, it would be interesting to test other approaches, including implicit communication, where agents infer information based on actions taken, or more advanced attention mechanisms to see whether they can improve performance even further.